First, I want to discuss the previous day's quiz. There was only one question in the for the last lecture, and the question was that 4 variables are used to represent a 4-bit binary number. When a certain numbers occur, a logical one should be generated, and the numbers are 1, 4, 5, 9, 11 and 12. Assume that complemented variables are also available, then reduce the expression. So, the numbers are for which the output should be 1, the decimal values are 1, 4, 5, 9, 11 and 12. So, first we convert the decimal to numbers to binary. So, 1 means 0001, as already it is mentioned, it is a 4 variable function. Similarly, 4 is 0100, 5 is 0101, 9 is 1001, 11 is 1011 and 12 is 1100. Now, the terms will be, or the mean terms will be, 0 means complemented variable, 1 means uncomplemented. So, 0001, that means for decimal value 1, it will be A dash, B dash, it will be B dash, then C dash D. So, it will be B dash, C dash D. Similarly, for 4, it will be A dash B, C dash D dash. For 5, it is A dash B, C dash D, 10101. For 9, it will be A, B dash, C dash D. 11, 1011, so A, B dash, C, D. 1 means that as for A, C, D, that particular mean term and the binary values, it is 111. So, there the 3 variables are uncomplemented one, and as only the 0 it is for B, so it will be B dash in the mean term. Similarly, 12 will be 1100 means A, B, C dash, D dash. So, these are the terms. So, that means in the expression that the sum of these mean terms will be there. So, F will be that, if first this will be the expression, that means that previous terms, all the previous terms will be there, and these are the 5 terms. Now, if we draw the Carnot map, then that there are, for these 5 mean terms, there will be 5 such, there are 6 mean terms, there will be 6 ones, and these are the positions. Now, if we do the couple or quad or the octet, whatever be the thing, so here it will be only couple. Say if we see that these will be, it will be one couple, these will be one couple, these will be another couple, and this will be a couple. So, there are 4 couples exist. Now, if we put that thing, then the sum will be that B, C dash, D dash plus A dash, C dash, D plus A, B dash, D. Why these are 3? Because see here 1 is already covered. That means, say when we have we have considered one couple here, we have considered one couple here, then already this one is covered in the A dash, C dash, D, and here this one is covered in the B, C dash D dash. So, this is actually a redundant one. So, this easily we can reduce, and that is why there are only 3 terms, and this is for the A B dash D. Okay, this term is for the A B dash D. So, we got the expression that A B dash D, and for the previous 2 couples B C dash D dash plus A dash C dash D. Now, we start the today's thing, that how we can cover the hazards by Carnot method. Now, first thing is that what do we mean by hazards and what is the reason for hazards. Now, in theory, or so far we have discussed in the previous classes, we assume that ideal switching characteristics for all gates, or the operator that we have considered, that AND, OR and the inverter, there we have assumed that it is a ideal switching. That means, when it is, what do we mean by switching? Switching is that when it is changing from 0 to 1, say it is that some value, one variable A, it is changing 0 to 1 or 1 to 0, then it is taking almost no time. So, this is a switching, and we call this is a ideal switching. But in practice, the propagation delay is associated with each logic gates. Means, when say this is a AND, means if it is, it can be a AND gate, this can be a say simple case 2 input AND gate, or this can be a dot operation. Now, whatever be the thing, say I am taking, this is a 2 input AND gate, or this is a dot B, say A dot B operation. So, Z equal to A dot B operation. Now, in practice or in real life, it will take some time. Now, this we are calling the, for gate we are calling this time is the gate delay or the propagation delay or propagation delay. Now, similarly, if we consider this operation just to execute this A dot B, it will also take some time, and that is also the delay of this takes some time, that is called the delay. So, that we are calling that each logic gate is associated with some delay. Now, each waveform has finite rise and fall times. What do we mean? See, so just now what we have drawn, see whether it is a AND gate or whether it is a inverter, it is taking some time to do this operation, to do this AND or to do this inversion. Okay. Now, say ideal switching means, say if I take that this is a, say here it is a 0 to 1, 0 to 1 switch, here it is a 1 to 0 switch. Now, this is the ideal situation, as if this 0 to 1 or 1 to 0, it is not, almost it takes no time. So, I can tell that takes no time for this switching. but in real life situation this state actually it takes some time. Then again here it will be like this. That means here it starts, but at least it takes this amount of time. So here this is the time it needs for this rise, and this is the time it needs the fall. So these we are calling the rise time, this we are calling the fall time. Now in real life it is some time. If this is the x axis is the time axis, then it takes some finite time for this switching, either from 0 to 1 or it is from 1 to 0. Now for this reason that as each gate is taking some time for its execution, or what we have defined as a delay, and sometimes this creates a problem in real life circuit. Let us take an example and of hazards. So this problem we are defining as a hazard, and that this is the reason for the hazard, that the time or the delay it is taking. So let us take an example. Say Z equal to AC plus BC bar. This is a 3 variable expression. Now if we draw the Carnot map for this expression Z, then how we see? Say our thing is that here I am taking that the upper portion, I am taking the AB variable, and this is my C variable. So here the 4 terms will be A dash B dash, A dash B, AB AB, AB AB dash and C dash C. So for AC term, AC plus BC dash. So this can be a, say here for AC dash, this can be a realization. See here this is for BC dash, means for this couple, this represents BC dash, and this represents AC. So this is my BC dash and this is my AC. Now if we draw the logic circuits, see this is a 2 AND gate whose inputs are A and C, and B and C dash. So C dash I am taking as if the input is coming from C, and by introducing a inverter in between. So this input is actually, this is C, this is C bar. So this is my C bar, and this is OR. That means this is my F equal to AC plus BC bar. Now see here, when that AC is for the first gate or the top AND gate, when it is executing AC, then just to compute C bar, because for that gate delay associated with the inverter, it will take some time to compute this thing. So when this input of the OR gate is available, say this is my F1, this is available, that time F2 is not available, because this inverter is taking some time to compute C bar, and then BC bar is computed after some time for this delay, and again some delay is associated with the bottom AND gate also. So, F2 will be there, but think that when F1 is available, that time some signal value is available here in this line, that means the second input of the OR gate. Whether it is a correct F2 or not, that we will see, and if it is not a correct F2, then it will give a problem, and that we are telling as this is the hazard of the circuit. Now, if we see the timing diagram or the timing chart of this particular circuit, say I am taking A and B, both are high. So, this is, that means A equal to 1, this is A equal to 1, here B equal to 1. Now, C is switched because C is the input of both the AND gate. Now, initially C is high. Now, here C is taking some value, say set C is, here C is falling, C is falling. Now, as for the delay of the inverter, immediately C dash will not be available or C dash will not be computed. C dash will be available after some time, say it takes this time. So, actually C is fed here and C dash is available, say this is my C dash. So, in between this time, that means when C switches or C becomes 1 to, if C is 1, C dash becomes 0, or when C switches to 1 to 0, and for C dash becomes 0 to 1, in between these, that output of the F, there will be a glitch in the output of the F, and these we are defining as a hazard. So, if we consider the timing chart, this is the reason why we are getting a undefined output or not the correct output at this stage when the C is switched. Now, again if we take another small example, say one AND gate, this is one AND gate where whose inputs are A and X, and another inverter where simply X is being inverted. So, this is my in output X complement, here this is my X, and this is again AX, this is AX. Now, what will happen if, see there, if the delays are different or if the delays are same, the delays of this AND gate and the delays of this inverter, because the output of the first AND gate and the output of the inverter are the two simultaneous inputs of the next AND gate. So, if the two delays are same, initially first we think that these two delays are same, then same time this AX and the X complement are available and we will get a correct output F. So, there will be no hazard in the circuit. Now, if the inverter this inverter has the delay which is greater than this AND gate, then first this AX will be available first, but this X complement is not, it is delayed, so it is not. Or the reverse thing can happen, that AND gate has more delay than the inverter. Then what will be the timing chart? Or if we draw the timing diagram of this particular example, then see, first again I am taking that my A is high, this is my A equal to 1. Now, say this X, initially the X is 0 and now it is being 1. So, it is switching X equal to 0 to 1. Now, what the X complement? The initially the X complement will be, this is 0 to 1. So, this becomes X complement, it was high, and ideal situation it should be, here it should be 0, but it should take some time for the inverter delay. So, it will take this time, it will take this time. So, this is the time it will be taking for this transition, or to make the X inverted or the output of the inverter to be stable. Then in this case, in this particular example, at the output F, there will be a glitch when this, for this transition or in this period. That means, if I consider that this is my output F, then I will get a glitch at this position. So, this is a static hazard. This is a now, what we are discussing, that how we can eliminate the hazards, the elimination of hazards by K-map. See, the hazards can be eliminated by including the redundant implicants. So, in this particular example, glitch occurs as the C changes from 1 to 0. So, already we have seen that if C changes from 1 to 0 and when A plus B equal to 1. So, or what we can tell that A equal to, or instead we can tell that A equal to 1, B equal to 1, and then if C changes, there will be a glitch occurs or the hazard comes. Now, see that our example is that Z equal to AC plus BC bar. Now, this is nothing but a multiplexer type of example. That means, whenever A equal to 1 or B equal to 1, my output Z or F should be, this should be 1. So, it should be independent of C or C bar. That means, if C equal to 0, see the type of function, if C equal to 0, then the second term is 1. If C equal to 1, then the first term is 1, and as it is a odd function, so 0 plus 1 is 1 or 1 plus 0 is 1. That means, if it is a 0 plus 1 is 1 or 1 plus 0 is 1. So, whatever be the value C takes, 0 or 1, that Z should be 1. That means, it is independent of C. Now, this particular property we can utilize to reduce the or to make the circuit hazard free. And how we can do that thing? We can include another input AB, or this is actually a redundant implicants. Now, see, again here we consider the Carnot map. Now, earlier we have seen this is AC plus BC. So, this is one couple which represents the BC dash, this is one couple which represents the AC. Now, there is another redundant implicant, that is my AB, and what earlier we discussed, particularly by K-map or that Quinn-McCloskey, that this redundant implicant can be ignored, so that it can be further reduced. So, now what we are again we consider, what we are doing again we consider that this implicant AB. So, now the implicants are AC, AB and BC dash. So, what will be the circuit? See that this is AC, AB, BC dash. There are 3 main terms and this is a sum of product forms. So, AC, AB, BC dash. So, whatever be the value of C or C dash, C or even the C switches from 0 to 1 or 1 to 0, actually it is immaterial, because if the OR gate properties or the truth table of OR gate is that if any one of the input of the OR gate is 1, then it will, the output will be 1. So, that means if A equal to 1, B equal to 1, that means AB high, then one input is high. So, it is immaterial what the first input, what this first input of the OR gate or the third input of the OR gate, this first input of the OR gate, say it is F1 or the F3, whatever will be the situations, that means F1 or F3, whether they are 0 or 1, that means I am telling this is a do not care theta, theta can be 0 or 1, anything. So, it only depends on AB. So, by including the implicant AB, I can easily reduce the hazards. So, by doing this thing, we can, this is normally called the static hazards. Now, we take another example. See here the previous example is already included here. So, this is BC bar, this is actually C complement. So, BC bar, the first AND gate is computing, the bottom AND gate is computing AC, that means BC bar plus AC, and here C is inverted, being inverted as C bar. So, these OR gate, so this is nothing but our previous example, that F, it is giving the F. Now, I have included another sub component, say another inverter. This is one inverter whose input is C bar. So, this is actually input is C, and another AND gate is included. So, this is FC. So, it is nothing but FC. Now, if we consider the timing diagram, see that first again I am considering that A and B are high, that means my A equal to B equal to 1. Now, the complement of C. So, initially the C is 1, now it is switching 1 to 0. this is 1 to 0. Now, what will be the F? Already we have seen that it is a static hazard, that means I will get a glitch during this transition. So, this is a glitch I will get. Now, what will be the G? See that G value is that during this transition again it will be some delay, and H again that where the F was there, that time it is a some glitch will be. That means for this particular circuit with the static hazard also some more hazards we are getting. See here F we are calling this is a static hazard. Now with this hazard also for this particular circuit, when we have incorporated or we have included another inverter and the AND gate, then we are getting some more added glitch. See this one for the H, this is a some more one for this. This is called the dynamic hazards. Now, what is the reason for dynamic hazards? Unless in the circuit that static hazard exists, or if say we would not get the glitch in this F line, then we would not get there will be no glitch in the H line. So mainly this is that as the static hazards exist in the circuit, and that is why that some dynamic hazards, that means some more added hazards with the static hazards we are getting, and this we are defining at the dynamic hazards. So dynamic hazards can only exist as a result of static hazards, and we need not be concerned with dynamic hazard if static hazards are eliminated. So that means in the previous cases that if these glitch are not there, if these glitch are not there, then there will be no glitch in the H also. So in the H also there will be no glitch. Now if we summarize that the hazard covers by K map, then what we get, that the minimal circuits may not be hazard free, as the example we have taken, and the minimization have to be sacrificed if we want hazard free circuits. That means in real life, if we want a reliable circuits, that means which is not giving any hazards or it is not producing any glitch at its output, then sometimes we introduce, intentionally we introduce some redundant implicant to reduce or to overcome the hazards, or to get a more reliable circuit. And by using this Carnot map we can easily include this redundant implicant. Now today we read another thing that is called the variable entered map. So far we have discussed that normal K map, then the how we can reduce that extra implicant or the Quinn-McCloskey. Now today we read that one is variable entered map. See why another variable V map is, or variable entered map, or normally it is called the V map, why V map is needed. Normally that Carnot map we have read that is very good for, or very suitable, well suitable for the 6 variable function. If it is more than 6 variable, then to draw that thing is a cumbersome one. So we need to automate the program. Now for larger, for n variables, say when n is a very big number, for larger numbers, this is not a good choice to reduce the function by a k-map. Then the variable entered map can be used to plot an n variable problem on an n minus 1 variable map. So, if we write program, then always for a large value of n, we can reduce the k-map for its lowest values, or that some reduced variable map, and this is a very big advantage. So, it is possible to reduce the map dimension by 2 or 3. So, that means if n is 8, then I can reduce it by 8 to 7, then from 7 to 6, 6 to 5, like that. So, it will be very good for writing a program and for large variables, and the design involving multiplexers can readily be solved by this approach. So, this is another big advantage. That means, if my design problem involves the multiplexers, means just now the examples we have discussed, that type of AC bar, AC plus BC bar, that type of equation or function, then it will be very good to select or to choose the variable entered map. So, now we see that what do we mean by, or how it differs from the normal k-map. We take one example. So, plot the k-map for z equal to a dash b dash c dash plus a b c dash plus a b dash c dash plus a b c. Now, see that again, if we or see here, if we draw the normal Karnaugh map, see, first thing is that see, this is that variable or the Karnaugh map for that ABC. So, see, this is a 3 variable function where ABCs are there, and for the first 3 terms, see, for the first 3 terms, that C dash is there, means these are complemented form, and only in the 4th term this is a uncomplemented variable for C. Now, see, if we draw so this is for my AB now see z equal to 1, so this will be my A dash and A, this is my B dash and B. So, this is my A dash B dash. Now, see, this is if C dash equal to 1, that means if C dash exists in the term, then this will be Z equal to 1. See, the previous example, A dash B dash C dash exist. See here, A dash B dash C dash is one of the mean term. So, that means if A dash B dash is true and C dash is also true, means C dash equal to 1, then the output will be 1, because this is a sum of mean terms. That means again if we realize this is nothing but a 4 input OR gate, and if any one of the OR gate is 1, any one of the input of the OR gate is 1, then it will be output will be 1. So, this Z will be 1. So, in this way what we can tell that this is actually my A dash, B dash, C dash. So, if I see, this is a 3 variable function, but I am drawing it for as if 2 variable A, B, and I am taking C as my variable or map. I am telling this is map entered variable. Map entered variable MEV. So, this is the position that or this element that Z equal to 1 or output will be 1 if A dash, B dash, C dash, that means the first term. Now, this is my A term. So, this is my AB dash. Now, Z equal to 1 if C dash equal to 1, that means some A, B dash, C dash, that min term is there. We check whether it is there or not. See, A, B dash, A, B dash, C dash, A, B dash, C dash. So, that min term is there. So, this is Z equal to 1 if A, B dash, C dash, that term is there. Similarly, there must be one term that when Z equal to 0, that means this is A dash, B, there will be no term, and Z equal to 1 if C dash equal to 1 or C equal to 1. So, that means this is the min term for this element is the AB, that means ABC dash and ABC both exist in the expression. So, from here what we can tell that my expression must be some Z is for the first element, this is A dash, B dash, C dash, because my C dash is the variable or map entered variable. Then for the second one, this is A, B dash, C dash, plus, see, for the third element it does not exist because output will be 0, that means the min term does not exist. And then for the fourth one, actually this the term is from the K map, this is AB term, and as both C dash and again C both exist. So, that means AB C dash plus ABC. So, this will be the thing. Now, we can reduce this thing by this. Say this is a map and A dash A, B dash B. Now, we can reduce as if this is the first one is C dash, means the output will be 1 if this is A dash, B dash, C dash. Again this is the output will be 1 if the C dash is true, and here output will be 1 if C or C dash is true. That is why C plus C dash, or means plus. So, C plus C dash. So, as if in the normal K map these were actually either 0 or 1. If the min term exists, then that particular element we put as a 1, otherwise it is 0. Now, that 1 is replaced by either the third variable, which I have not considered in my map. See, actually there are 3 variables A, B, C. I have considered only A and B are the map variables, and C as if C or C complement or some combination of C, that means C or C dash. Just now we have seen, because both the term exist, ABC dash or ABC. That means it will be true, the output will be true if ABC exists or even ABC dash exists. So that's C plus C dash. So the 1 will be replaced by the third variable in this particular example, or the complemented variable, or the OR of the variable and its complemented one. So this third variable, which we have not considered in the variable of the K-map, and the 1 is replaced by this variable, this is called the map entered variable or MEV. So this is called the map entered variable or C in this particular example. This is map entered variable. In this particular example it is C and it is called the MEV. Now we take one 4 variable example. Say ABCD are the 4 inputs and output is Z. First we consider the truth table of this 4 variable function. So truth table means that all possible combinations, all 0 0 0, 0 0 0 1 to all 1 1 1, I have to take the what will be the output. That means that all possible input output combinations I have kept. That is the truth table, the tabular representation. Now see, this is the, for this particular function, that if say I have kept ABC are the K maps, and that means I have taken my D as the map entered variable. So this my D, it is the map entered variable. Now when ABC is, actually we should draw a line here. Say ABC is as 0 0 0, then D can be 0 or 1, Z is, if D is 0, Z is 0, if D is 1, Z is 1. Then how I can represent this? See, ABC 0 0 0 means A dash, B dash, C dash, this is my term 0 0 0, and see, if D is 0, output is 0, Z is 0, if D is 1, Z is 1. That means my output is nothing but the D. So for this, that A dash, B dash, C dash, this is D. Now so actually this is my 4 variable function. If we draw the normal Carnot map, it should be a that 16, that means 4 by 4 table, 4 by 4 map. Instead of that, we have reduced it into 3 variable. I have taken ABC as the normal variables and D as the map entered variable. So now for that, so this is for the first one. So this output is Z is nothing but D. Z is nothing but D. Now for the second pair, see, for 0 0 1 means A B, A bar B bar C, A bar B bar C. Then this is, if D is 0, Z is 0, D is 1, output is Z is 0. That means it does not depend on the D, or it is independent of D. that means my output is 0. Similarly, here my output is 1 for this combination. So, this is the combination that A bar, B, C bar. Earlier previous one it was A bar, B bar, C. This is A bar, B bar, C bar. This is A bar, B, C, and this is 0 1 1 0 means it is actually complemented of D bar. Complemented of D bar. Now again for the next pair, if we draw, see for the next pair, actually this is for the term A, B dash, because this is 1 A, B is 0 means B dash, and C is 0 means C dash. See, D is 0 1, Z is also 0 1, that means my output is D. Then for this term it is A, B dash, C, and my output is 0. Similarly, this is for A, B, C dash. This is 0 1, D is 0 1, then out Z is 1 0. So, this is complement. And for A, B, C, this is 0 1 and this is C. Here I have written theta, means this is actually do not care, it does not. Here also actually I have taken theta, theta means this term will not appear. So, whatever be the case, it will not be the thing. Now, if we summarize or if we put this truth table, from this truth table what we have studied, that means for each pair or for each mean term consisting of ABCs, how the output Z depends on D. That means what we can tell, that variable entered map is for the combination, for each combination of its reduced variables, how the output depends on its map variable or map entered variable, that we are summarizing or we are putting in the map. So, just now what we have discussed, this is the summary. See, for that A dash, B dash, C dash already we have seen, this is D. For the next, this is A dash, B, C dash. A dash, B, C dash, it is 1 or D plus D dash. Similarly, for A, B, C dash, this is that last cases, that A, B, C dash, that it depends on D theta plus D dash. Theta is the do not care. Similarly, here A, B dash, C dash, it is D plus D dash theta, and we have seen that A dash, B dash, C, for this mean term, actually whatever be the D value, the output will be 0. Similarly, for A, B dash, C, the output will be 0. For A dash, B, C, the output will be D dash, and for A, B, C, it does not, it do not care, whatever be the combination of A, B, C. So, that is why we have kept theta. So, this is the summary. That means, for the 4 by 4 map, see, it is reduced to 2 by 4, that means from 4 variable to 3 variable, and as if this 1 0 are reduced by some combination of the other variable, the rest which is left, which we have not considered in the kernel map. So, this is the concept of the map entered variable. So, this is another example and of the 4 variable, and see here simply that's a D we have considered as the map entered variable. So D is MEV. Then again that if we take AB and C, then see for A dash B dash C dash it is D. See for this term A dash B dash C dash it is D. Similarly, if I take say A dash B C dash, A dash B C dash, so it is D. This is ABC dash D. So ABC dash D. So ABC dash, if D is true, that means for this it is D is true, if D is true. Now see A B dash C dash, the first term, the A B dash C D and A B dash C D dash. So these two terms exist. If for A B dash C term, it is true whether it is D or D plus D complement. So that means for A B dash C, the term will be D plus D dash. See, this will be D plus D dash. So in this way we can summarize our this being map. So now what we can do, that now we can reduce in the same fashion. Now we can take the couple, we can identify some couple. See here, I can, this one be a couple, this can be a couple, and this itself is a couple because D plus D dash is there. See for the first one and the fourth one, these two. So we can easily reduce this expression by again considering the couple. So what we have seen, by introducing or by selecting the VMAP method, that we can easily reduce the n variable to n minus 1 variable, and recursively we can do that n minus 1 to n minus 2, and so it will be very easy for reducing some expression when some higher variables, a large number of variables are there. So we'll now today's quiz problem, that using D as the MEV, reduce Z equal to A dash B dash C dash D plus A dash B C dash D dash plus A dash B C dash D plus A B dash C dash D dash, A B dash C dash D dash plus A B dash C D dash plus A B dash C D plus A B C D dash. So actually this is a 4 variable function, and as this is a 4 variable, so normal K map should be this type of 4 by 4. Now it will be reduced to the 2 by 4, and the way, so and this as D as the MEV, so here it will be, the content will be, it will be A, B, C, and the content will be some D complement or some D plus D dash, or the combinations of D theta, D dash. So this is the today's quiz problem, that we have to reduce using the MEV method. Thank you.